Bismillahirrahmanirrahim. Greetings. In the previous 4 lectures, we discussed about irrationality of a square root of 2. I discussed that subject at the level of basic algebra and college algebra audience. Now, this lecture, the contents of this lecture is going to be preliminary for the coming 1 or 2 lectures in which we are going to go over, prove or discuss the irrationality of a square root of 2 again, but analytically. Now, let's get started for today's lecture, shall we? Now, I start with bounded set. A set is bounded, roughly speaking, if it has a finite size. Now, with the word size goes distance. And with the word distance goes metric spaces. And that subject belongs to the real analysis, so we are not really going to dive that deep into this subject. So I have some examples and I put them on the bulletin board and we go over them in writing. So let me zoom that and prepare it for that. May I do that, please? Okay, let me stay out of the way and we go over it that way. Now, S is a subset of real number, and the set that we are dealing with, in fact, real number is a field. Now, this set S as a subset of R is bounded if and only if there exists M and M in the field, in the set of reals, such that for all the elements in this set are kind of trapped between M and M. So if this gives you a little bit difficulty, because mathematical definitions are condensed and to the point, of course, and that they give you a little bit difficulty for the beginner. If you have difficulty with comprehending the abstract sounding definitions in mathematics, try to make example of your own, and then follow the definition through that example. That example will help you a lot to define it without trying to memorize it. So this is my advice for you. Now let's look at a few examples. Now here, the open interval from 1 to 2 and the closed interval from 1 to 2, both of them are bounded. Both of them are bounded above and below. The difference is that this set does not include its least upper bound, that I'm going to define what that means, and does not include its greatest lower bound. Again, I'm going to say about these two both shortly. But this set does contain them. Now, going to this set from negative infinity to 1, it is bounded above. And what is the upper bound? Elements of the upper bound are, if it is parentheses, which means if 1 is not included, the upper bound starts from 1, go to infinity. And if 1 is included in this set, again upper bound starts to go from 1 to infinity. Similarly, we can define this set to say that it is bounded below. You follow me? And then this set from negative infinity to positive infinity, the entire number line, is not bounded, neither bounded above nor bounded below. Okay. Now let's go to the next one. Next one, I have a few examples. I go over maybe 1 or 2 of them and leave the rest of them for you to see. I don't need to go over all of them. So let's go over, let's this one, the first one, shall we? Sorry I don't have a board to go over that and be a bit more. Let me see if it is zoomed. Looks good. Okay, let's now discuss about this one. Here, the set, open interval from 1 to 2. It is bounded above and below. The upper bound of this set, excuse me. The upper bound of this set is all the numbers 2 and above. Now, the 2 is not included in this set, but 2 is an upper bound for this one, that later we talk at least upper bound of that I haven't defined it yet. We will go over that shortly. So now consider this set. Now this set from 2 to infinity is bounded below. 2 is not included, so the greatest lower bound out of all the lower bounds, 2 is the greater than all of them, so we call 2 as the greatest lower bound. So it is bounded not above, but it is bounded below, and the greatest, greater than all of the lower bounds is 2, we call it greatest lower bound. You follow me? And the very same goes with this set. This set is from negative infinity to 1. Here, 1 is not included. The upper bound of that includes 1 and goes to infinity. Do you follow me? So it is bounded above, but it is not bounded below. So the rest of them I don't have to go through. I just leave it for a few seconds. You can pause also with your computer and go over them yourself, what they mean. So now let's go to the next one. Let me see if it is zoomed. Looks good. Okay. Now, let's see what the least upper bound that I mentioned a few seconds back. Another name for that is supremum, what that means. Now, here, let me see if I need to cover. Not really. Now, we have two sets, S1 and S2. On the number line, the interval from 1 to 2, not including 1 and 2. And then second one is from 2 to infinity. Okay? Now, let me just read for you. Every x in S2 in this set can be considered as an upper bound for this set, for S1. Now, the smallest of all the numbers in S2, the smallest of all of them, is called the greatest lower bound for this set. And the smallest of all of them, which is 2, is the least upper bound for this set. You see, the name says it all, least upper bound, which means out of all the upper bounds, 2 is what? Is the smallest, but 2 is not belong to this set. So there is least upper bound. There is an axiom for that indicates, I'm going to bring that one up shortly, that 100% a set that is bounded above does have least upper bound. You guarantee that by an axiom. All right? All right, now let's go to the next one. Next one is really nothing new. We have already talked about it, just another repetition. Because with repetition, especially for the students, the best way to learn is through repetition. Okay, now let's talk about this one. Now here our number line, and we have two intervals, one from 0 to 2 and the other one from 2 to 4, and neither of these two intervals, they include 2. You follow me? So the least upper bound for this set, for this interval from 0 to 2 is what? Is from 2 to 4 in this case. And that least upper bound of this set is the greatest lower bound of this set. So this set does not include its greatest lower bound, and this set does not include its least upper bound. You follow me? And the rest of them I have written for you if you like to pay more attention. And also here, it's very important to know this one, is an axiom that says every non-empty subset of real number, which is a field, that is bounded above, possess a least upper bound in R. Do you follow me? So when you read that, also look for the counterexample to see if there is any set or there is a field that does not include its least upper bound. As a matter of fact, I wrote that one. This is true for the reals, but this is not true for the set of rational numbers. Q usually is selected to represent set of rational numbers. So this axiom is very, very important, very in fact important. All right, now we will be using, definitely we will see this axiom in the coming lecture, or lectures. Now let's go to this one. Is about Archimedean properties. Now, this again, I'm using them because this is a preliminary. We need all these terms and terminologies we will be using in the coming lecture. Now, depending on the mathematical system that we are using, which is under consideration, the Archimedean concept can be classified as an axiom. We can say it is an axiom. We can say it is a property, or we can even say it is a theorem, because some of them we can prove it. We have proof for that. So in our case, in our lecture, there are different versions of them that in reality they are a paraphrase of one another. They are kind of equivalent, but they are saying a little bit different ways. We are going to go through that. And this Archimedean theorem is, I call it theorem in fact, but here we call it properties in our lecture. Okay, now let's go a little bit more into this subject about Archimedean. Again, we need that one for the coming lecture. Let me make sure it is zoomed and is readable. I could make it a little bit more. Okay. Now again, we are in the subject of Archimedean. Now, two numbers we can say, x and y, both of them are positive. Then there exists n in n. N is usually this notation is used for natural number, has become kind of a standard. So there exists n, some natural number, in the set of natural numbers, such that if you multiply by one of them, will be greater than the other one. So if x is already bigger than y, he didn't mention which one is larger, then n will be 1. Is that right? Just trivial. If x is smaller than y, then there is an integer, in case positive integer, a natural number, that if we multiply by x, we will exceed y. Do you follow me? And when we are multiplying by a natural number, means this number of times we are adding this to itself. And when we add and add and add, it will exceed this one. All right? Now, I have written the particular case of that. I don't have to go. Now, let's go to this part of it. And let me also cover this one. Now, what that means, what I just went over, means that the natural numbers is not bounded above. That's what you say. So any number you give to me, I can multiply that two numbers you give to me, I can give you an n such that if you multiply by the smaller will be larger than the larger. That can keep, no matter how far those distance they can be from each other. So again, that means there is no such a bounded, and also there is no infinitely large number. That's what it really means that. So now let's go back to this one. An example I have. An example is that x equal to, let's say, 2 minus L squared. I brought this one up purposely because we will be seeing that in the coming lecture. As a matter of fact, that's all we will be talking about, these two. So our x is this, and L stands for least upper bound, and y will be this, is another, this is number. This is a number and this is number, so this is an example that we can apply for that. Do you follow me? Okay, then the next one, because I said there are kind of different versions of Archimedean property, or theorem we can call it, some of them, is that epsilon usually in mathematics is used for extremely small number. So it says given epsilon positive, which means no matter how small it is, I can determine for a natural number, a rational number, such that 1 over n is smaller than e, smaller than epsilon. That means usually there is no infinitesimal. But in non-Archimedean is also another good subject to study. He shows that there are even numbers, give us to the rational function, that is to the left of 1 over n, to the left of it, which means it goes, in reality, it says there is no such a thing as infinitesimal in what is really saying that. Okay then, so this is hopefully clear to you. Now make some example for yourself if it is difficult. For example, let's say epsilon is 1 over 10 to the 10. Which is extremely large, extremely a small number. Then what will be n? N will be 1 over 10 to the what? 10 to the 11. N will be 10 to the 11. That's a natural number. So 1 over 10 to the 11 is what? Is less than 1 over 10 to the 10. So no matter how small epsilon is, I can always give you an n, which is a natural number, that 1 over that n will be smaller than epsilon. You follow? It's very, very simple grade school logic, really. Pause and think about it for a second. You know, don't memorize and take anything for kind of granted. Okay, now let me go to the next one, if I may. The next one is now, given two numbers, x positive and y positive, then I wrote that there exists a natural number, n, a natural number from the set of natural, such that if you multiply by what? By the smaller one will be larger. I'm just repeating that one. So let's look some example for that. For instance, if x is 5 and y is 19, x is smaller than y in this case. Then what is n? N is 4. Well, if you multiply 4 by x, you get what? You get 20. if you add 4 of them together, 5 plus 5 plus 5 plus 5, will exceed this one, which is 19. Do you see that? Okay, now next one is about epsilon that I already mentioned. I've gone over this one already. So I leave for a few seconds, I pause it, then you can look for that. Okay, then let me go and zoom this one back, say a few words, and be close to this lecture. Huh? Okay, as I mentioned, I'm repeating myself that for the coming lecture or lectures, we will be going and discussing about irrationality of square root of 2 analytically. Okay, then I thank you very much for watching. I hope that my lectures are beneficially, and if you have any topic or subject you want me to give a lecture, please mention it in the comment section below, and I will be happy to prepare such a lecture for you. And also, if you have any comments, suggestion about my teaching, please do also mention that one in the comment section below, because there is always room for teaching enhancement. And you will be doing a favor to me to make me a better teacher, and also a favor to your fellow student, because I will be giving better lecture to them, so they will be benefiting better. Okay, then I thank you very much again for watching, and as always, I wish you all prosperity and good health, and please stay and remain healthy. So long.